Welcome to Math with Mrs. Bibb. Today we will be solving systems of inequalities and then using that to work with optimization with linear programming. A system of inequalities is a set of two or more inequalities with the same variables. So a set of two or more inequalities with the same variable. The intersection of the graphs is called the feasible region. So the feasible region is the intersection of the graphs. Ordered pairs ordered pairs, I'm capitalizing that for a reason. Ordered pairs within the feasible region are viable solutions the feasible region may be bounded if the graph of the system is a polygonal region or unbounded if it forms a region that is open. So the feasible region is an intersection of the graphs. Ordered pairs within the feasible region are viable solutions. The feasible region may be bounded if the graph of the system is a polygonal region, or unbounded if it forms a region that is open. And you should write down everything that I have written down for that definition for feasible region. We're going to solve the system of inequalities, and I am going to give you that system, so if you'll write that down first. My first equation is y is less than or equal to 4x minus 3. And my second, it's not an equation, I shouldn't have said equation. My second inequality is negative 2y is greater than x. We're going to make sure they're in slope-intercept form. The first one is, the second one is not, so I am going to divide by negative 2 to make that be in slope-intercept form. So I divided by negative. I need to flip the inequality symbol over. So y is less than negative 1/2 x. So I can name the slope and the y-intercept for each of these. The slope is 4 for this first one. The y-intercept is negative 3. I will draw a solid line because it's equal to, and I will shade below the line. So if you will please make sure to write that. That is your work for this particular problem. For my second line, I am going to have a slope of negative 1/2, a y-intercept of 0. It will be a dotted line and I will also shade below the line. Okay, I am going to do the top one in yellow. I'm going to graph that one in yellow, and I'm going to graph the bottom one in green. And I'll shade with the appropriate colors as well. Okay, so I am going to graph the yellow one first. Y-intercept of -3, so down 1, 2, 3. Rise 4, run 1 to the right. Rise 1, 2, 3, 4, 1 to the right. 1, 2, 3, 4, 1 to the right. 1, 2, 3, 4, 1 to the right. And I'm going to go the other direction. 1, 2, 3, 4, 1 to the left to try to help myself draw a better line. And this one is solid. And I'm going to shade below that line. Below would be underneath it here. So I'm going to shade the whole thing. Then I'm going to graph the second one. I'm going to graph that one in green. The y-intercept is 0. I have a slope of -1/2. So rise 1, run 2 to the left. Don't like where that landed. Rise 1, run 2 to the left. 1, 1, oops. Did it again. Rise 1, run 1, 2 to the left. Rise 1, run 1, 2 to the left. Rise 1, 1, 2 to the left. You could also go down 1 and 1, 2 to the right. Then I'm going to draw this dotted line. And I'm going to shade in green. And my solution will be where the yellow and the green intersect. So shade below the green dotted line. So hopefully you can see that this region here, I'm going to highlight the region in red, that's the solution. That this region here is where the shading intersects. So the red will be my solution. Sorry about that. So my my viable solutions would come from, this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So my viable solutions will come partly from quadrant 4 and quadrant 3. And this is not, the red portion does not make a polygonal region, so this one is said to have a feasible region that is unbounded. That's what an unbounded feasible region looks like. So if you'll please make sure to write that down. And there's no writing the solution. The solution is the red shading. So make sure you have your shading, make sure you have different colors on your notes for that shading. Example 2, I have 3 inequalities. The first one is y is less than -4/3 x plus 5. The second one is y is greater than or equal to x minus 2. And the third one is x is greater than 1. All of them, except the last one, are in slope-intercept form, and the last one you cannot put in slope-intercept form. So I can go ahead and name the slope is -4/3. The y-intercept is 5. It will be a dotted line, and I will shade below that dotted line. For the second one, the slope is 1. The y-intercept is -2. It will be a solid line because it's greater than or equal to, and I will shade above that solid line. And then the last one, this is a vertical line. When you don't have y, it's a vertical line, and it's going to be dotted on x equals 1. And we will shade to the right. The numbers to the right of that are greater than 1. Okay, let's start. I'm going to graph this one in red. I'm going to graph this one in blue. And I'll graph this one in yellow. And then I'll shade with those corresponding colors. And the solution will be where those colors intersect. So I'll start with the red. My slope is -4/3. My y-intercept is +5. 1, 2, 3, 4, 5. So there's my y-intercept. I'm going to rise 1, 2, 3, 4, run 1, 2, 3 to the left. And did I do that right? 1, 2, 3, 4, 1, 2, 3. No. Hold on. 2, 3, 4, 5. Then I'm going to rise 1, 2, 3, 4, 1, 2, 3, put a dot. Then I'm going to go down 1, 2, 3, 4, 1, 2, 3, put a dot. 1, 2, 3, 4, 1, 2, 3, put a dot. And it is a dotted line. So I'm going to make it dotted. Doesn't matter how many dots or dashes you have, as long as it's dotted. And I'm going to shade below that line, so let me grab a red highlighter. Going to shade below. So my solutions are either going to be in quadrant 2, 3, or 4. Oh, and 1. Can you see that? Part of it is in quadrant 1 too. So all of the quadrants are represented by these solutions. Let's see what happens if we're restricted in just a minute. Okay, the next one, I'm going to graph the y-intercept of -2, -2, and I'm going to graph a slope of 1. Rise 1, run 1 to the right. Okay, then I'm going to draw that line. And I'm going to shade above that line in blue. So now still all 4 quadrants are represented. Same size for quadrant 1, but just limited the size for quadrant 4. It's limited to this region right here. Quadrant 4 is only shaded here. Quadrant 1 shaded here. Most of quadrant 2, it's just missing this piece. And a big piece of quadrant 3 is being shaded. Now I'll graph that last one. It's a vertical line on x equals 1. So here's 1. And it's a vertical dotted line. So I'm drawing a vertical dotted line on x equals 1. And then I'm going to shade to the right. To the right. So that definitely limited where my solutions are at. And hopefully you can see, I know it's really hard to see, but hopefully you can see that. Let me see if I can find another color. Green. Oh no, I already had green. I'll do black. So hopefully you can see that the shading intersects in this area. Whoops, I need to make that thinner. In this area right here. And that is a bounded feasible region. So I will write the feasible region is bounded. You can tell that this one is bounded because it makes this shape right here. it makes a triangle. So it has 3 points that bound that polygonal region. That. For linear programming, Example 3 says, a Niagara Falls boat tour company charges $19.50 for adult tickets and $11 for children's tickets. Each boat has a capacity of 600 passengers, including 8 crew members. Suppose the company's operating cost for one boat is $2,750. Write and graph a system of inequalities to represent the situation so the company will make a profit each tour. Then identify some viable solutions. The first thing you should always do when you're working with word problems is you should define your variables. So let's do that. X is going to represent the number of adult tickets. I like to use X and Y. Y is going to represent the number of children's tickets. And then I can write my equation. I need to figure out, I'm going to grab a highlighter. I need to figure out, put all the people together. So 600 passengers, including 8 crew members, plus the X and the Y. So it can hold a maximum amount of 600 passengers. So less than or equal to 600. X plus Y plus 8 is less than or equal to 600. Also, we have to make sure, and I should have used a different table here, but we have to make sure that the number of adult tickets is greater than or equal to 0. And I don't know why I chose an A, it's an X. Sorry about that. And the number of children's tickets is also greater than or equal to 0. And then let's put all the money together. The company wants to make a profit, so that means they want to make more than $2,750, and they're selling their tickets at $19.50 for the adult tickets, plus the children's tickets are $11. So $19.50 times X plus 11 times Y. We want that to be greater than $2,750. I think what I'll do, and you may want to do this too, I'm going to get rid of the X and the Y axis. I go back and draw it in lightly. I apologize, I didn't look ahead and think to do this. Wow, that's still too dark. So this will be adult tickets. And this will be children's tickets. And I'm going to go by 100s. Okay, so I'm going to graph this first one in blue, the second one in red, the third one in black, and the fourth one in green. So the first one in blue, I'm going to subtract 8. and subtract x. So y is going to be less than or equal to negative x plus 592. Okay, my scale, this is going to be, let me grab the black really quickly. This is going to be the x-axis, and I'm going to go by hundreds, and this will be the y-axis, and I'm also going to go by hundreds. So that tells me my scale. All right, so I'm going to graph 592 for a y-intercept. So 1, 2, 3, 4, 5, almost 600. And then I'm going to do a slope of negative 1. So I'm going to go down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. You get my drift. And it can only go from here to there. And it is less than or equal to, so we're looking at just this region here. Then x is greater than or equal to 0. I will use red. That means the y-axis. X is greater than or equal to 0. And y is greater than or equal to 0. So both of those are still in this region, and I'm not going to grab a different color to highlight. We're still looking in this region. And then I'm going to graph the last one in green. I'm going to subtract 1950, so 11y, oh, I'm highlighting, sorry, 11y greater than negative 1950 x plus 2,750 divided by 11. So when I do that, I get the values 96 over 55x plus 250. So my slope is 96 over 55, and my y-intercept is 250. Now I'm going to graph, but as I look at this problem, graphing the green one, as I look at this problem, it's a little tougher to graph with the slope. So I found the y-intercept of 250. So 100, let me grab my pointer. 100 is here, 200 is here, and 50 will be halfway between those two. So 200, 250. And then I found the x-intercept by substituting 0 in for y, and I did 2750 divided by 19.50, and that gave me 141. 100 is the first one, 200, so kind of in the middle. And then I'm going to graph a dotted line. So that green is a dotted line. Let me grab a highlighter to graph the slope, not the slope, the shading. And so my shading is going to be greater than. So that means the shading would be up here, all in this region. So all of this is colored in. Sorry, I'm not taking my time. The most important part here in a system of inequalities is the intersection. So hopefully you can see, maybe I'll shade with black, that the intersection is in this area here. I'm trying to shade with black, but it doesn't really look like black. Is in this, it looks like a trapezoid, sort of. I'll outline it with black also. So this dotted, oh, it's back to green, but that's okay. And here, and here. So it's outlined in green. Then it says, write and graph a system of inequalities, which I did. And then identify some viable solutions. So some viable solutions would be any solutions that are within this shaded region. So this solution would work. You can't tell what that dot is. Let me try yellow. Like that solution would work. This one, this one, this one. So let me name some of those yellow dots. This first yellow dot that I drew would be 100, 100, 200, 300. So 100, comma 300. And I'm going to name what those mean here in just a second. And let me do that second yellow dot I did. 200, 200. The third one I did is 200, 100. Should label this as viable solutions. And then one more I'll name 300, 100. And then what do these mean? 100, the X value is the number of adult tickets, and the Y value is the number of student tickets. So what these things mean, this first solution is that 100 tickets, 100 adult tickets, and 300 student tickets. I guess I should say children, not students. Children tickets should be sold for the tour company to see a profit. And I won't write all of those. We'll just do the first one. Let me highlight that. So 100, 300. And so all of those mean the same thing. 200 adult tickets and 200 children tickets have to be sold for the company to see a profit. 200 adult tickets, 100 children tickets, and 300 adult tickets, 100 children tickets. So those are all viable solutions because they fall within this shaded region. I have it reversed. Sorry about that. So we're going to define linear programming, then I'll go back into that previous example. Sorry about that. Linear programming is a process of finding the maximum or minimum values of a function for a region defined by a system of linear inequalities. Process of finding the maximum or minimum values of a function for a region defined by a system of linear inequalities. That is linear programming. And this would be like a business application in which you would use graphing inequalities and finding their solutions to maximize your profit or minimize the loss. So let's go back and read that example. In linear programming, we already defined that. Process of finding the maximum or minimum values of a function for a region defined by a system of linear inequalities. Example 4 is a linear programming problem. We are going to graph all of those. One thing I want you to notice is that one of those problems listed is not like the other. So if you'll look at those just for a minute, which of those problems is not like the other? And hopefully you said it was this one. This is a linear function to be maximized. So what we'll do is we'll graph the other three solutions, not solutions, sorry, the other three inequalities, and then we'll look for the points of intersection. We'll want to see if our feasible region is bounded or not bounded, and we'll determine that in just one moment. Okay, so this first one. This is two vertical lines. One at x equals -2 and one at x equals 4, and you shade between. So please do write that down. And let's go ahead and do that, and I'll graph in blue. So at -2, and it's solid because it's equal to, hope your lines are a little straighter than mine. And at +4, 1, 2, 3, 4. And then I'll grab the highlighter and shade between. So only solutions that are between these two vertical lines can be considered. Once we've graphed the other two, we may be able to eliminate more solutions and narrow it down. Of course, on the SAT, you could use Desmos and type this in, but we're not going to use Desmos here. You're welcome to use Desmos to check, but we're not going to use Desmos here. For this one, my slope is 1. My y-intercept is 2. It'll be a solid line, and I'll shade below. Okay, so y-intercept is 2, +2. I'm going to do a rise and run of 1. Rise 1, run 1 to the right. Rise 1. And I'm going to continue that until I intersect those initial vertical lines. It is solid. And shade below. So the shading would be here. You could always fast forward through my shading. Once you see where it's going to be shaded, you could always fast forward. I think I would. Pause and then fast forward. Okay, so there's the second one. The third one, let's do in green. My slope is -1/2, even though it's written as a decimal, it's -1/2. My y-intercept is -3. It's going to be a solid line, and I'm going to shade above. So my y-intercept is -3. Go to the origin, go down 3. 1, 2, 3. And then I'm going to rise 1, run 2 to the right. Rise 1, run 2 to the right. Do that a couple times. Go the other direction. Go down 1. Oh, did you all hear what I said? Rise 1, run 2 to the left. So sorry. Rise 1, 2 to the left. Rise 1, 2 to the left. Then I'm going to go down 1 and 2 to the right. Down 1, 2 to the right. And do that a couple more times. And then a solid line through those dots. And I'm going to shade above. And that sort of looks like a mess, and I'm shading where I shouldn't be shading. Oops. I've got to figure out where all of this shading, the blue, the red, and the green, where they all intersect, what shape. Since I don't have any dotted lines, I am going to grab a black marker here in just a moment, and I'm going to outline where that shading intersects. Hopefully you see it beforehand. Just be very careful. It has to be all of them in which it intersects. Okay, so I'm going to trace along this line, the red line I had. I'm going to go down the blue vertical line I had. So hopefully you're seeing this polygonal bound region. This is a bound region. Let me keep going. And here. So that is definitely a trapezoid. The shading is in this region bounded by this black trapezoid. Now, here's what I need. I need to find the corners or the ordered pairs of the polygon shape formed. So there are 4 ordered pairs. From the origin, I'll go left 2, so -2, 0 is one of them. And then I'll go left 2 from the origin, down 2, so -2, -2. From the origin, I'll go right 1, 2, 3, 4, and up 1, 2, 3, 4, 5, 6. So 4, 6. And then I'm going to go to the origin and go right 1, 2, 3, 4, down 1, 2, 3, 4, 5, it looks like. 4, -5. I'm going to use that linear function. That's what we're optimizing. And then I'm going to put those values, the maximum and the minimum values. So these are our values, and of course we know the maximum is the highest and the minimum is the lowest. So I'm going to substitute, let me highlight, I'm going to substitute -2, -2, 4, and 4 for x. And I'm going to substitute 0, -2, 6, and -5 in for y. -2 times -2 plus 6 times 0 is 4 plus 0, which is 4. That's the first one. The second one, -2 times -2 plus 6 times -2 is +4 minus 12, which is -8. The next one, -2 times 4 plus 6 times 6 is -8 plus 36, which is 28, I think. Yes. And the last one, -2 times 4 plus 6 times -5 is -8 minus 30, which is -38. And now I need to name the maximum and the minimum values. So I'll name that down here. The maximum value, let me look at the values, I haven't looked. I've got 4, -8, 28, -38. So the maximum value of 28 occurs and that doesn't look right. OCC, I think that's right. Occurs at 4, 6. The minimum value, so the smallest number over there, of negative 38 is at 4, negative 5. Okay, so that's how you do an optimization problem. I think we have one more. I have written all of the inequalities and the function equation that goes with this particular word problem. I want to go through it with you quickly so you can see where each of these came from. The 30 square feet here is the total amount of space that Avery has to create this garden. The 2.25 is the amount of space, 2.25 square feet, cucumbers will take up, and that's why X is the number of cucumber plants. And then the 1.5 is the amount of space that each lettuce plant will take up, so 1.5 Y, and that's why Y stands for the number of lettuce plants. It says that, let's see, she wants to grow at least 4 of each type, so that's why X is greater than or equal to 4, Y is greater than or equal to 4. And she wants to grow at least 16 plants in total, so X plus Y greater than or equal to 16. So that's where all 4 of those came from. The function to be used is the amount of water that it takes for each of the plants. It takes 25 gallons of water over the lifetime of a plant to water cucumber plants, and then it takes 17 gallons over the lifetime of the lettuce plant to water that. Next, I'm going to graph these inequalities that I have listed here. So I will pause and graph over here. Okay, I have figured out all of the values here, and these are the values that I'm looking for to try to figure out how many of each plant, so this is what I'm looking for, how many of each plant Avery should plot in order to minimize her water usage. That probably should say plant. How many of each plant Avery should plant in order to minimize her water usage? So if you look at the values, I've got 304, 338, 336. That's how much water would be used. So the smallest value is 304. That means that 412, that intersection, gives me the least amount of water usage. So that means that Avery, here's my final answer. Avery should plant 4 cucumber plants and 12 lettuce plants to minimize the water usage. So should plant 4 cucumber plants and 12 lettuce plants to, and I'm going to have to finish this up here, minimize her water usage. And that is all of this set of notes. I hope you have a wonderful day.